Hello dear students, today we are going to find out the moment of inertia of a circular disc. The introduction to the concept of moment of inertia as well as its physical significance has already been discussed in the class. Today we are just going to derive the expression for the moment of inertia for a circular disc. Now for this case, let us consider that we have a circular disc like this, okay, and the circular disc is having a radius capital R, and here we will consider that the total mass of this particular circular disc is capital M. I will provide the notes for this particular section of the derivation in the Google Classroom, so you can relate it along with this video lecture. So now we are going to consider a small elementary ring of radius x. Okay, so this is a disc, so we are considering an elementary ring like this, and this is again of radius x, and this elementary ring is of width. You can consider that the width of this elementary ring is dx. So this is a elementary ring. We have considered a small part of the disc, circular disc, so it will definitely come in terms of a ring, and this particular ring is of width dx. Okay, now if I ask you that what is the area of this particular ring, then you will have to say that the area of this particular ring will be actually this perimeter. The circumference is, since the radius is x, the circumference will be twice pi x. So area of the elementary ring of radius x is equal to 2 pi x and its thickness is dx. Okay, so we know that total mass per unit area of the whole circular disc is equal to, total mass is capital M and total area of the disc will be equal to pi r square. Since its radius is r, so it will be pi r square. So this is the mass per unit area of the whole disc. Now we know that the area of the elementary this ring is of thickness x and radius radius x and thickness dx is twice pi x dx. So this particular shaded area, this ring that we have considered, the mass of this ring will be, therefore mass of the elementary ring of radius x and thickness dx is equal to, so this is the mass per unit area. Alright, so this is mass per unit area and this is the area of the ring, so it is twice pi x dx. So we have this. So let's see what are the things that will be cancelled. This pi and pi gets cancelled. Okay, so we have simply twice m by r square. Obviously m and r square is a constant for the particular disc, and we have x dx. Alright, so this is our, say, question number 1. Therefore moment of inertia of the elementary ring, okay, about an axis passing through its center and perpendicular to its plane is equal to. Now you know that moment of inertia is nothing but mass into distance of the square of the distance from the axis of rotation, distance of the element from the axis of rotation, distance of the element from the axis of rotation. Now in this case the mass is basically, when we talk about mass, this mass is basically given by this part. Okay, so it is twice m by r square x dx. So it is twice m by r square x dx. So this is a mass and we need the distance square. Okay, so this is the distance square. So what is the distance? Is the distance from the distance of that element from the axis of rotation. So distance of that element from the axis of rotation, in this figure you can see that, in this figure we can see that this particular element is at a distance x from the, this particular element is at a distance x from the center of that particular center of the disk, that means from the center of the axis. Okay, because in this case we know that the axis is passing through its center. So the axis is basically like this. If I draw this diagram like this, if this is a center, so this is the axis. Okay, so this is your element, small element, that ring we are considering of radius x and thickness dx. So this particular ring is at a distance x from this particular axis, because the axis is passing through the center of the circular disc. So this axis here, so this distance is going to be x square. So we have 2m r square x cube dx. Okay, so this is the, so you can say that this is the moment of inertia of that elementary ring. Okay, but you know that this elementary ring is not the whole ring. So we need to add so many elementary rings like this, like this, like this. Then only we can get the whole disk. Okay, so we need to integrate this amount for the total value of x to get the total moment of inertia. Therefore, suppose that this is the equation number 2 we have got. Okay, this is so therefore moment of inertia, okay, of the whole circular disk is equal to, okay, so we will denote it by I. So is equal to, simply we will have to integrate this thing. Okay, so we will be doing 2m by r square x cube dx. So we need to put a lower limit and upper limit. Lower limit and upper limit of what? Of dx, sorry, x, because we are integrating with respect to x. So what is the x? In the diagram you see x is nothing but the distance of the ring from the center. Okay, so if you look at this, if you start from here, let me change the color. Okay, so if this is the center and if you start from here, you need to go up to this. So if I ask you what is the minimum value of x, so you need to say 0, because it is 0 at the center. And if I ask you what is the maximum value of x, it will go up to radius capital R. So this is actually 0 and this goes to capital R. Okay, so since you know that 2m by r square is constant, so it will come out, so it is 0 to r x cube dx. Okay, so as everyone know that, so this is 2m by r square x cube, means it will be x to power 4 by 4, and we need to put the lower and upper limits. Okay, so we have 2m by r square, so it will be like r to power 4 by 4 minus 0. Okay, now you know that this 2 and 2 gets cancelled, so this r square gets cancelled, so we have half m and r square. So this is the moment of inertia of a circular disc, okay, about an axis passing through this center and perpendicular to its plane. Okay, so this angle, this is a condition, this is case A. So we will call it that this is the case A. So this is a moment of inertia of the disc about an axis passing through its center and perpendicular to its plane. So second case is that, so case B is basically we need to find out the circular disc is the same mass, same radius, okay. But in this case, what's the difference? In this case, we need to find out the moment of inertia about the diameter. Like this is the diameter, sorry. Okay. So this is the diameter and this is the diameter. Okay. So any diameter you can take. This is also a diameter. Okay. This is also a diameter. Right. So basically we are going to find out. Sorry. Okay, so right now we have a circular disc of mass m, and now we are going to find out the moment of inertia with respect to this and with respect to this. Suppose let me call it like I can call it as A dash, and say this is called B dash. Okay, so already we know that if the moment of inertia about an axis perpendicular to its plane and passing through its center, we already know. So we can look at this diagram like this also. Okay, so this is the center. We already know about this. Now they are asking you to find out the moment of inertia about the diameters. So this is one of the diameter, and so this is one of the diameters. Okay. So about this, what is the value? Half m r square. Okay, so about this is the value. Okay, now we need about this and we need about this. Okay, now according to the perpendicular theorem of moment of inertia, what is the statement about this moment of about that theorem is that as we have already discussed, that moment of inertia of a plane lamina about an axis perpendicular to its plane is equal to sum of the moment of inertia of the lamina about two axes at right angles to each other in its own plane intersecting with each other at a point through which the perpendicular axis is passing. So that means moment of inertia of the particular circular disc about this axis should always be equal to sum of the moment of inertia of the disc, okay, about two perpendicular axes, okay, about the two perpendicular axes pass, and they should be lying on the same plane as that of the circular disc, and they should also intersect at a point through which this particular axis is passing. Okay, so from that point of view, if I call it I, if I call it IA, if I call it IB, say this is I, this is called moment of inertia about is called IA, moment of inertia about is called IB. So according to perpendicular axis theorem, I should be equal to IA plus IB, okay, because these two are what? Perpendicular to each other, okay, and they are again intersecting at a point through which this particular axis is passing. But we know that due to symmetry of that particular disc, what will happen? Due to symmetry of the circular disc, IA will be equal to IB. So I is basically equal to I is basically equal to IA plus IA. Okay, so that's equal to twice IA. So therefore IA is equal to half of phi. So half of phi means half m r square. So what remains? 1 by 4 mr square. So this is IA. So therefore IB is also same. So that will also be equal to 1 by 4 mr square. Okay, so this is a case B. Okay, so now there may be another case. So in the same way you will have to do for some other geometrical configuration, not only for circular dish, you may have to do it for cylinders, you may have to do it for spheres. Okay, now we have case C. So what is that case? Case C is about suppose you have a circular dish same as mass m, capital and radius capital R. Now you need to find out that the moment of inertia about a tangent. My diagram may not be that good. I may not be drawing exactly circular dish. Okay, I have. So this is the thing. So now as of now from the case B, we know what is the moment of inertia of a particular circular disk about the diameter. You know it. So that value is equal to 1 by 4 mr square. Now I am asking you what is the moment of inertia about a tangent. Okay, so suppose that, let me call it say IT tangent. Okay, so now there comes parallel axis theorem. Okay, so again let us, you just go back to your notes if you have written in the class. So there, according to parallel axis theorem, what is that theorem? That moment of inertia of a particular body about any axis like IT, about this particular axis, is equal to sum of the moment of inertia of the body about a parallel axis passing through its center of gravity and multiplication of or product of its mass and the distance between the two axes. Okay, if I call it, so this, if this is of radius r, so this is also r, this is also r. Okay, so we have, according to parallel axis theorem, suppose if I call it as IA, so it will be IT is nothing but, according to parallel axis theorem, IA plus m r square. Okay, so IA is nothing but 1 by 4 m r square. Alright, which we have already obtained in case B. Okay, and then we have m r square. So it will be 1 by 4 plus 1 m r square. So that is equal to 5 by 4 m r square. Alright, so this is a moment of inertia of the circular disk about the tangent. Okay, so we have three expressions like this. This one is 1. Okay, so then we had this also about diameter, and this one is about an axis passing through its center and perpendicular to its plane.